All right, hello and welcome to the first application that we'll go through. So we're going to be studying a quick example of choice under uncertainty. Okay, so first we're going to consider an agent who is facing a choice between three possible alternatives. Okay, and so these alternatives could be anything you like. They could be consumption bundles, they could be political leaders that you choose. But because it's choice under uncertainty, we're going to make things interesting and we're going to use typical examples. And so these alternatives are sure thing alternatives. That's an important thing to know. And we're going to label them X, Y, and Z. And so you can think of X as ice cream at the beach on a rainy day. You can think as Y as being just staying home and reading a book. And you can think as Z as the same as X, except it's sunny. So it's going to be ice cream at the beach on a sunny day. All right. All right. So these are the three alternatives in the choice set faced by our rational agent. And we're going to be asking, how does he or she compare lotteries over these three sure thing alternatives? Okay. So we're going to denote as px, py, and pz a lottery over these three alternatives. Okay, and what does this lottery mean? This lottery means that with probability px, x is going to realize, with probability py, the alternative y is going to realize, and with probability pz, the alternative z is going to realize. So this is going to be the lottery over the set of alternatives in our feasible set, right? Okay, so the idea is that a lottery is going to give a probability for all the alternatives, but it could be that, let's say you decide to drive to the beach and you don't know too much about the weather. It could be that the lottery is only over two alternatives. You just assign a zero. So for example, 1/2, 0, 1/2 is a lottery that represents the idea that you're going to drive to the beach, and with probability 1/2 is going to be rainy, and with probability 1/2 is going to be sunny. And with zero probability, you're staying at home, right? Another example of a lottery is a sure thing. So for example, 0, 1, 0 is a lottery that represents, it's exactly identified with the alternative Y because it's basically the lottery over a sure thing. It assigns probability 1 to the alternative Y. All right? So our goal is kind of to understand how to model expected utility theory in this context. Okay? So to do so, we need to be able to have a preference ordering over lotteries, and we're going to use the preference ordering over alternatives to achieve this. Okay? So first, let's put a little bit of conditions. Because px, py, pz is a probability distribution, we need the following requirements. We need each of these probabilities to be between 0 and 1. And we have something that's redundant, is that because the sum of the probabilities is going to be exactly equal to 1, we can rewrite that pz is exactly equal to 1 minus px minus py, right? We don't need the extra notation. Okay, so one question could be, does the rational agent prefer, for example, this lottery with probability 3/4 they're going to the beach on a rainy day, with probably 1/4 they're staying at home, to, for example, this lottery, or even this lottery, right? So in order to answer this question, we need to have a ranking of the sure thing alternatives first. And if we have such a ranking, we can use the utility associated with the sure thing alternatives to get a utility for each lottery, right? So let's look at our alternatives again. And here we kind of want to say that ice cream on a sunny day is going to be strictly preferred to ice cream on a rainy day, right? Now, depending on the type of person you are, you might prefer staying at home than going out to the beach. But here we're going to say that Z is also strictly preferred to Y because you like going out at the beach on a sunny day. But you really don't like getting soaked on the heavy rain, so we're also going to say that Y is strictly preferred to X. Okay? So here we have a clear preference ordering where Z is the most preferred outcome, which is strictly preferred to Y, which is strictly preferred to X. So note that here we don't have any indifference point. So here the notation that I used is slightly different. And if you would compare it to the notation used in class, I believe it would be with a P. Let me check real quick. Yeah, the strict preference is written with a P. All right, and so let's assume that our least preferred outcome, X, gives the agent a utility of 1. So our sure thing alternative, X, gives the agent a utility of 1. Then let's assume that staying at home when it's staying dry gives a utility of 2, and going out at the beach gives a utility of 4, right? Then here, the way I would evaluate each of these lotteries above is going to be to use expected utility theory. And the idea is that the utility of the first lottery, 3/4, 1/4, 0, is going to be equal to the probability times the utility from the outcome associated with each probability. So it's going to be 3/4 times u of x plus 1/4 times u of y plus 0 times u of z, right? So in other words, with probability 3/4, I'm going to get the utility from x, which is 1, so I'm getting 1. And with probability 1/4, I'm getting the utility from y, which is 2. And with probability 0, I'm getting the utility from z. So in total, this is 5/4, right? Then the second lottery, I'm going to use the same principle. I'm going to compute an expected utility, so a weighted average in some sense, of the utilities over the different alternatives. So here it would be 1/4 times u of x plus 3/4 times u of y, plus 0 times u of z. And this would be equal to 1/4 times 1 plus 3/4 times 2, which is equal to 7/4. So I prefer staying at home than going out to the beach on a rainy day. So I prefer the lottery but which only assigns positive probability to the first two outcomes to give a higher probability to my preferred alternative. Okay? But what about this one, which gives some positive probability to the two extreme alternatives? So here, the utility from this lottery, again using the expected utility framework, would be 1/2 times u of x plus 0 times u of y plus 1/2 times u of z. And this would be equal to 1/2 times 1 plus 1/2 times 2, which is equal to 3/2, right? Which is equal to 1.5. And this is equal to, actually I made a mistake, sorry, this is 4. And if this is 4, this is going to be equal to 4/2 plus 1, so 5/2, which is equal to 2.5. And this here is 1.75. All right, so, and this here is 1.25. So here, with the preference ordering over the short things here, illustrated by these utilities, so this is a cardinal assignment over my ordinal ranking. This is an ordinal ranking, but here I'm assigning a utility value. I can order the lotteries, and I can say that the third lottery, because the payoff here, 2.5, is larger than 1.75, the third lottery is strictly preferred to the second, and the second lottery is strictly preferred to the first. All right? So the rational agent would prefer this lottery first, so driving to the beach and not knowing whether it's going to rain or be sunny with probability 1/2 and 1/2, to this alternative, staying at home most of the time with certainty if I go to the beach with probability 1/4 it's going to rain, to this. All right? All right, that's it for today. We'll do the prisoner's dilemma next time.